Today we will work through the concept of moment generating functions. The goal is going to be to introduce moment generating functions and study some of their preliminary applications. Let's begin with the basic setup here, which is x is a random variable. We will assume it is discrete whenever we are in the need for simplification with PMF P of x. Then for n inside the set of natural numbers, the nth moment of x is defined as the expected value of x to the power n. This is also sometimes denoted as mu n prime, that is the expected value of x to the n. The nth central moment of x is denoted as mu n, and this is the expected value of x minus mu to the nth power. If we denote mu as mu1 prime, that is the expected value of x. We note that the variance of the random variable x is exactly the second central moment of x. That is, the variance of x is the expected value of x minus mu squared. Also note that the expected value can be considered or thought of as a good first guess for what the values of x might be. The variance of x is then going to be a good measure of the effectiveness of the expected value of x as a guess for the values of the random variable x. We note that when we are working with small variance, it would mean that the values of x are closely concentrated around the expected value, whereas a large value for the variance is going to imply that the values of x are more spread out away from the expected value of x. The nth moment of x as a result, that is the expected value of x to the n, is going to be a good guess for the values of the random variable x to the n. A question that is motivated by many other things in mathematics, but we will ask it anyways, is that if we knew the expected value for x to the n for all values of n, could we identify the distribution for the random variable x? Or, I mean, more plainly, could we identify the random variable x itself? Like most questions that we've been asking in the setting of these videos, it turns out the answer to this question is in fact yes. But before we talk about it, we will have to introduce the concept of the moment generating function of the random variable x. This is denoted by mxt, and it is the expected value of e to the t times x, provided that this expected value exists. What does this mean? It means that there exists an h greater than 0 such that the expected value of e to the tx exists for all values of t inside the interval minus h. Writing this out more explicitly, mxt is going to be equal to the integral from negative infinity to infinity of e to the tx times f sub x x dx when we are working with a continuous random variable. And it's going to be the infinite sum or the finite sum e to the tx times p sub xx when we are working in the context of a discrete random variable. If x has mgf mxt, then the expected value of x to the n, that is the nth moment, can be evaluated as the nth derivative of the moment generating function evaluated at t equals 0. We will be using this property a lot to calculate the nth moments of the random variable x. Let's work with some examples here. let's begin with the binomial distribution. So suppose the random variable x has the binomial distribution with parameters n and p. Then in this context, the PMF is defined as follows, and the moment generating function can be calculated as the series of the following calculations. So if we adjust the terms and notice that we can move the e to the tx into p to the x, we will notice that the moment generating function ends up being equal to p times e to the t plus 1 minus p, the whole raised to the power n. In this setting, let us check that the expected values and the variances can actually be calculated using the formulas for the derivative of the moment generating function. And as you can see here, the first derivative of the moment generating function evaluated at t equals 0 ends up equaling n times p, which is the expected value of the binomial random variable with parameters n and p. Also, if we calculate the second derivative of the moment generating function for the binomial random variable, we arrive at the following calculation. That is, the expected value of x squared ends up equaling n times n minus 1 times p squared plus n times p. And now we can combine this with the awesome identity for calculating variances, which is the expected value of x squared minus the expected value of x squared, to get the variance to be n times p times 1 minus p. Notice that this formula also lines up with the formulas that we have presented earlier for the variance of the binomial distribution with parameters n and p. Now let us calculate the moment generating function for the standard normal distribution, which has parameters mu equals 0 and variance equals 1. The PDF for this random variable is defined as follows, and we can calculate the moment generating function by writing out the integral 1 over square root of 2 pi times integral going from minus infinity to plus infinity of e to the tx times e to the x squared by 2 dx. Following through with these calculations, we will have to complete the square of the terms in the exponents, right? And we can pull out e to the t squared over 2 as a result, and do a change of variables where we will set u equals x minus t. Du ends up being equal to dx. X equals infinity implies u equals infinity. X equals minus infinity implies u equals minus infinity. And putting all of this together, we will get that the moment generating function for z is going to be e to the t squared divided by 2 times the following integral, which turns out is the integral of the PDF of the standard normal distribution, which is equal to 1. As a result, we get that the moment generating function for the standard normal distribution is exactly equal to e to the t squared divided by 2. We can now check that the derivative of this moment generating function evaluated at t equals 0 is going to equal to t times e to the t squared divided by 2 evaluated at t equals 0, which equals 0, which is exactly the expected value of the standard normal distribution. Lines up with what we expect. Also, you can calculate the expected value of z squared, which is going to be the moment generating function differentiated twice and then evaluated at t equals 0. Following through with this calculation, we notice that the variance will end up being calculated to be equal to 1, which is again what we expect. We will now talk about the uniqueness of moment generating functions of random variables. We state the important theorem here. Suppose we have two random variables, x and y, with cumulative distribution functions, capital F sub x and capital F sub y. We'll make two important assumptions. The first one being that all moments of x and y exist. That is, the expected value of x to the k and the expected value of y to the k exist for all k inside the set of natural numbers. The second important assumption is that there exists an epsilon greater than 0 such that the moment generating functions mxt and myt exist for all t inside the interval minus epsilon epsilon. In this setting, the moment generating function for x is going to equal the moment generating function for y if and only if the CDFs for x and y are equal for all values of u inside minus infinity infinity. And this is equivalent to saying that x and y are identically distributed random variables. This theorem says that the moment generating function completely determines the distribution of the random variable x. Of course, under the assumptions of theorem, the two important assumptions that are stated above. The second important theorem here is as follows. If x is a random variable with a moment generating function mxt, and y is a linear combination of x, ax plus b, where a and b are real numbers, then the moment generating function for y is going to be equal to e to the bt times mx evaluated at at. The proof of this theorem is quite straightforward, and we will write it out here. We start off by writing the equation for the moment generating function for ax plus b. And if you follow through with these integral calculations, you notice that this really simplifies to e to the bt times the moment generating function of x evaluated at at. We will now use the second theorem to calculate the moment generating function for an arbitrary normal random variable which has parameters mu and sigma squared. Recall that the moment generating function for the standard normal random variable was equal to e to the t squared over 2. And now to compute the moment generating function for x, we note that x minus mu over sigma has the standard normal distribution. As a result, we will have the random variable x as a linear combination of the standard normal distribution with parameters with a equals sigma and b equals mu. In this setting, using the theorem, we notice that the moment generating function for x can be calculated as the exponential of mu t plus sigma squared t squared divided by 2. We wrap up this video with the moment generating functions of some known distributions. The Poisson distribution with parameter lambda greater than 0 has the moment generating function mt equals the exponential of lambda times e to the t minus 1. The negative binomial distribution with parameters r and p has the moment generating function mt equals p times e to the t divided by 1 minus p times e to the t, the whole raised to r. The uniform continuous distribution over the interval a comma b has the moment generating function given by e to the t times b minus e to the t times a divided by t times b minus a. The gamma distribution with parameters alpha, the shape parameter, and beta, the scale parameter, has the moment distribution function given by 1 over 1 minus beta t, the whole raised to alpha, and this will be true when t is less than 1 over beta. A special case of the gamma distribution is the exponential distribution with parameter lambda greater than 0, and this has the moment generating function given by lambda divided by lambda minus t, and which is valid for values of t strictly less than lambda. Note that all of these calculations for moment generating functions that we have mentioned above are quite elementary. They involve basic integral calculations. Um, Also, we can use these moment generating functions to calculate moments of the random variable x. These are useful tools in applications. And finally, we will be using the moment generating functions of random variables to identify distributions uh, when we're proving some limit theorems later on in this course. For now, this is all that I want to talk about today. Just to recap, we spoke about the definition of the moment generating function and introduced two important theorems. The first one, which helped us to use the moment generating function to identify uh, or prove that two distributions are equal. The second one being the ability to calculate the moment generating function of a linear combination of a random variable whose generating function we already know. We saw these theorems in applications for a couple of distributions, and we finally stated a bunch of moment generating functions that we already know. This is all for now. Take care of yourselves, and I will see you around.